All right, so now we move on to lesson 18, which is gravitational field strength. Now, lessons 17 and 18 go hand in hand. In fact, when we think back to lesson 17 was all about if I take two objects with different mass or maybe the same mass, and these could be things like planets, they could be two objects on Earth, like two people standing next to each other, they could be planets moving around the sun, for example. There's some sort of force that is exerted between the two of those, and by Newton's third law, we get some sort of equal opposite force of attraction between those two objects. When we talk about a gravitational field, this is a different concept, but it has a lot of overlap, and we're going to see where those pieces of overlap are specifically when we go into the law of universal gravitation and where gravitational field strength exists within that. Now, right away, off the top of the notes, I want you to put GFS, indicating that when we talk about GFS, or when that's ever indicated in the notes as GFS, we're talking about gravitational field strength. Now, primarily, we need to make a distinguishing factor here. When we scroll down and we look at this idea within the notes of the concept of a field, it can be very broad. In fact, it's some sort of region of space surrounding a body, a charged particle, or a magnet which can exert a force on a similar body not in contact with it. Now, this can also be called an area of influence, and so you may also see that. Now, why is it that if I talk about a gravitational field and it has some sort of vector field, meaning some sort of way we can visually represent this, specifically of how objects interact with it, if I take a very small mass and I place it within the Earth's gravitational field, what happens? Well, what we would say is that there is some sort of area of influence. And within this area of influence, we're going to see that the object or that very small mass would then accelerate towards Earth's surface. Go. So within that area of influence, the Earth has a large mass, and therefore the object would accelerate towards the Earth, or towards the Earth's surface, or towards the center of Earth, if you really wanted to be fully correct. Now, we go into this idea of a small test or a small object known as a test object is used, and it's used to determine the magnitude and direction of the field. Why do we think that the object should be very small? Because we don't want it to affect the other object in terms of we don't want to have two large fields next to each other so that we can get some sort of combined magnitude of the field. Rather, we want to specifically get the field of the object we're considering. So specifically, it helps show the full magnitude of the area of influence. And there's so many ways we could say this because realistically, we just want to choose a small enough object or a test object that is relatively irrelevant in comparison to the object we're trying to measure the gravitational field strength of. Now, something I really want you to highlight in your notes is this piece here, and it revolves around defining direction and how we know direction that the object would move. If I take a test object and I place it in a field, what I experience to see, or what I want to see, is the direction and magnitude. And so if we place this object in, we can define the direction of a gravitational field as the direction the test object would move when placed in that given field. Now, that is an extremely important thing because when we look at the diagram on this next page here, I just want you to see how the overall vector arrows look and a couple key notes about this as we look into this. So near the surface of Earth, we know that objects would accelerate at this rate of 9.81. And we would typically say they accelerate downwards from our from our reference point, because we're looking at from the surface. If we're considering up is positive, down is negative, we would say that this is accelerating towards the planet. So it'd be going in the downwards direction at 9.81. Now, something we need to note is that as you move away from the center of Earth and you get farther and farther and farther, what's going to happen is that the magnitude will, or as you move farther away from the center of Earth, the gravitational field strength decreases in magnitude, but its direction remains unchanged. Yes, because what's happening is that let's now visualize this in two different ways. If I take the object, and I'm going to use like this object here, suppose it's close to the Earth's surface. I'm going to assume that this is close enough that the gravity experienced, or the gravitational field strength, is still 9.81. Now, what I'm going to do is take the object and move it out however many hundreds or thousands of kilometers. What I would then ask you is say, is G2 going to be less or greater than 9.81? Well, it should be less than 9.81 because now it's gone way out beyond, it's gone further out in this field. And so therefore, by the theory even talked about last class, the further the radius between two objects or the further the distance between two objects, we know that that leads to an exponential decay in the overall experienced force and what we're going to find to be the field as well. So what I would like you to do is to emphasize this even further and to go with a point that we're going to make very shortly here. I want you to just extend out these vector arrows. Now, something you're going to notice is that as these vector arrows go towards the center, the density increases. As the vector arrows go further away, the vector arrows space apart and they become less dense. And so as the arrows are more dense or closer to the middle, closer to the center of the mass, our gravitational field should be at a larger value. When we move further out and there's less density, we're going to see that that value drops. And so I'm just going to simply say it's less than 9.81 because I can't for sure say what it's going to be. Now, we want to go into this idea of let's calculate gravitational field strength based on the gravitational force equation that we established from lesson 17. Now, according to Isaac Newton, we get this idea of the universal law of gravitation is the following. Fg equals g m1 m2 over r squared. And what we can actually do here is we can create a familiar approach where we say, what if we know from previous lessons that Fg equals mg, which is equal to mass or of the acceleration of gravity? So you could either write it as ag or g, but most commonly we wrote it as the mg like this. Now what we're going to do is we're going to combine these two equations together and say that Fg is equal to Fg, or these two Fg's are equal, meaning we're going to set their products equal to each other. So now we have their products side by side equal to one another. And what I want you to see is that we have this where the masses are going to cancel out. M2, or the left M, cancels with the M over here, and therefore we get this acceleration due to gravity, or G, equal to AG, which is equal to G M1 over M2, or R2, I should say. Now, off in this margin here, what I'm going to recommend is that you do the following because it's really going to help us when we go to our next unit. In black, I'm going to write this. Same thing, Fg is equal to Fg. But now when we make the substitution, I'm going to make a very particular substitution. I'm still going to write it as mg, but on the right-hand side, instead of m1, m2, I'm going to write it as g capital M, lowercase m, divided by the radius between those two squared. Now, what I want you to notice is that you see m and m, these are both little m, or they're the other object. They're not the main object that represents the field that we're trying to measure. They're the object that is in relation to the field. They're on the outside, they're orbiting. They're like, let's consider this, the big M to be the Earth. Let's consider the little m to be like a satellite or some sort of test object that's going around it. In the grand scheme of things, this little m is not going to have an impact on the gravitational field strength, or it's not going to change our perception of the gravitational field strength. We want to figure out what is this g that represents Earth's gravitational field strength, or whatever specific mass is gravitational field strength. So this test object that we apply to it, or the little m, is really going to have no bearing on the overall gravitational field strength we're trying to measure. And so therefore, we can get g is equal to g from our formula sheet, or our gravitational constant, times capital M, which is the larger mass, divided by radius squared. This may be a way you want to start thinking about it, especially as we go into Unit C. I always recommend that we start seeing it as little m, big M, because then it makes it very easy to cancel the m that is correct in this case and leave us with that. But if you get this notation where we're going to go with this and say, okay, well, Fg equals Fg, and we treat it as this here where it's M1 and M2, and you know M2 cancels, great, no problem. I will say though, on your formula sheet, this is the way it's presented, is Fg equals capital G, M1, M2 over radius squared. So if you're more familiar with the notation from the formula sheet, there it is. But if you want to use big M, little m, that's also okay. And I think that that definitely helps. So the gravitational field strength can now be solved using this equation here. We can figure out how objects accelerate near any sort of specific planet or a specific object for that matter. All right. Now, we go into this next page, and we just want to make a couple notes here, specifically dealing with the diagram of vector fields. So we want to look at this and be like, the field lines can be drawn as the following, where we have a bunch of vector lines that condense as they go towards the center and spread apart or diverge as they go away from the center. We also want to draw the arrows going towards the surface or towards the middle of Earth, the center of mass. So that's really important, is to have all the arrows going down. Because if I had arrows going outwards like this, it would assume that the objects accelerate as they move away from the Earth, which we don't want to do. The field lines also tell us the following. The field lines can tell us two things: direction of the field and strength of the field. Those are two really important things. And strength of the field, again, is indicated by the density of those field lines. And then lastly, when we start looking at the test object that we place in it, the test object will always move towards the larger mass, because we're assuming that that test object is going to be something very small. It could be like, a pen in above Earth's surface, or a pen in relation to the outer kind of Earth. And we're saying, what is the object going to accelerate at, given that it's just like some pen or something like that? Okay. Now, in terms of this slide here, it's basically the same thing. In fact, it actually is the same thing. So don't feel like we have to dive into this too much again, because it was on the 2 pages ago. So we've already done that. No worries. What we want to look at, though, is right at the bottom here, and just make sure we formalize the equation that can be used to calculate gravitational field strength. Gravitational field strength can be calculated using this formula, and it's on your formula sheet again, just like the gravitational force or the force of attraction formula, Fg equals g m1 m2 over r squared. Now we have this gravitational field strength calculation, which is the following. Now, just to indicate this here, we would always consider this, and I always like to write this in the notes here, this would be considered the larger mass. So let's say we were like, they said, measure the gravitational field strength of Earth, and they give you the mass of some smaller object. Well, that smaller object's mass doesn't matter. We just want the larger mass, or the mass of the planet, we could even put it as there. And so typically they would say m, or in this case, I know it looks like a lowercase m, but ideally, if we wanted to do this, we could even say it's m1. That would be okay, or capital M. So maybe I'll do that below here. I'm going to write it as m1, just like it was on the formula sheet, or you can write it as g capital M divided by r squared, where the capital M, or m1, is the mass of the body creating that field. Really, really important there. All right. Now, let's actually go into just a first couple introductory concepts. And the first one, foremost problem that we want to look at is this one here, where it starts talking about how we compare newtons over kilograms to meters per second squared. The big comparable here, and the big thing I want you to realize, is that these actually represent the exact same thing. In fact, a newton over a kilogram is the acceleration, or is meters per second squared. And so when we calculate this, let's actually just prove that we can go between them and then they actually represent the same thing. First, what I'm going to do is say a newton is equal to, well, a newton is representative of a force, and more importantly, we could consider it to be the F net over the overall force that's happening in this situation, which is equal to mass times acceleration, which in our case is equal to kilograms multiplied by meters per second squared, just as we've known before from kinematics, or even the beginning of dynamics. Now that we know what a newton is, let's sub that in. Newton divided by a kilogram is equal to kilogram times meters per second squared divided by a kilogram. Now, what you're going to notice is that the kilograms in the numerator denominator go away, and I'm left with meters divided by seconds squared. So we really need to see that these two, newtons over kilograms, is paralleled or equal to meters per second squared. And as long as we know that these two are connected moving forward, then regardless of which one we put in our solution, they would both be correct in my opinion, unless they specifically ask for one or the other. All right, use the general formula for gravitational field strength to calculate the GFS at the surface of the Earth. Well, here we go. That's our first exposure to GFS, or gravitational field strength. As soon as they ask for this, I want you to go to your formula sheet and get this value, or get the formula that you're going to need. G is equal to capital G, big M, which is M Earth. And you could even designate it as this, G Earth. And I'm going to erase this just to create more space here. So gravitational field strength of Earth is equal to the gravitational constant times the mass of Earth divided by the radius of Earth squared. You can get really specific with these things. If rather than just writing them as like blank, you want to write them with variables, this is a very mathematical way, or a very university level approach, is just making sure you're being specific with what variables you're talking about. Now, our gravitational constant comes from the back of the formula sheet, capital G. Mass of Earth comes from the formula sheet, or would be a given value. And these are all in the back of the formula sheet, by the way, in the constant section. And the radius of the Earth is also given as a constant value on the back of the formula sheet. So we can actually figure out all these values very simply. Gravitational field strength of Earth is equal to G, which is 6.67 times 10 to the negative 11, newtons times meters squared divided by kilograms squared. Make sure you put all the units in there. The mass of the Earth is equal to 5.97 times 10 to the power of 24 kilograms. And then this is all divided by the radius of Earth, which is also on the back of the formula sheet, 6.37 times 10 to the power of 6 meters squared. Now, again, the number one thing everybody forgets, or most people will forget, is this squared here. I said this back in the lesson 17 video as well. This squared in the denominator is very easily forgettable, so please make sure that it's included there, or else your number will be drastically different than it should. Now, let's show a little bit of unit cancellation here. When we cancel our units, the kilogram squared cancels with one of the kilograms in the numerator. Our meters squared go away, and this takes away the meters squared from the numerator. Therefore, we're left with newtons over 1 kilogram. Now, the gravitational field strength of Earth, without even touching a calculator, if this is near the surface of Earth, well, when you type this into your calculator, you should get 9.81 meters per second squared. But instead of saying meters per second squared, I actually want to say newtons over kilograms first and foremost, and then say 9.81 meters per second squared. Because if you look at the problem, you're going to realize that when we did our cancellation, we didn't get meters per second squared, we got newtons over kilograms, which then becomes meters per second squared. So if anything, like just based on the pure calculation and how things cancel, I would write newtons over kilograms first. But if you put meters per second squared, you're not technically wrong. In fact, I think that's great. All right, now moving forward here, what we want to look at is the following. Gravitational force, which is lesson 17. I really want you to put this below. Lesson 17, which is equal to Fg. It was all about solving for the attractive force between two objects, or the attractive force between things on Earth or celestial bodies or whatever it might be. The attractive force in newtons, and you can include that in brackets as well, is not equal to the lesson 18 material, which is gravitational field strength. This is a measure G, which is a measure of newtons over kilograms, which is also equal to meters per second squared. Clearly, these things are not the same thing. And rather than lesson 8, it needs to be 18. So I'm going to make sure I'm specific on that one. Lesson 18. There we go. Lesson 17, which is newtons or a force, it's a push or a pull between the planets, is not equal to gravitational field strength, which is an acceleration of objects within contact of these objects. Now, to avoid that confusion, we're just going to make sure we highlight those key notes from below. So some confusion might exist between gravitational field strength and gravitational force, but just remember that each of these would associate differently. Each experiences the same gravitational force, but in this case of these, we need to make sure, and I'm going to erase this line here just to avoid confusion of what I'm saying here. Gravitational force is that attractive push or pull. Gravitational field strength, when we look at gravitational field strength, there's an important note to measure about that, and we're going to use the below just to help us show this here. So suppose we consider the following, and you could draw connecting arrows to all three of these. So let's say I connect these two to then I connect this one and this one. These are all connected to the same thing. Now, what I want you to recognize is that the values of these are not equal. And these all represent different forces. One has a force, another has a different force, another has a different force. Why are they different forces? Because they all have different masses. This one has a distinct mass, this object has a distinct mass, the third object has a distinct mass. And if objects have a distinct mass, it means that the force they experience, or the force, this push or pull that's experienced, is going to be larger for things with more mass. So the cart that's being dropped versus the box that's being dropped versus the ball that's being dropped, we would expect that that cart with the most mass or the most matter composition will experience the greatest amount of force when dropped and is in this field of gravitational field strength of Earth. Now, what we want to make sure is that when we look at these, they're all experiencing the same field though. And it's important to note that below. All experience the same field. That is G, and I'm going to put that below here. G is 9.81 newtons per kilogram, which is also equal to 9.81 meters per second squared. Really important to note that there, because although we get different forces, that's just because of the different masses. We do experience the same field though. Now, going on to our final note, we see a very common relationship between our Fg and our G, or our force of attraction and the gravitational field strength. Both of them follow the inverse square relationship, or more importantly, as I change the radius, the impact on the force of attraction and the gravitational field strength is the same. And what I want you to do is, off to the side here in the margin, can we write two things in here? First and foremost, can you write Fg, and then can you write G below that? So on this axis, we're going to see that we have one symbolic of Fg, one that is symbolic of gravitational field strength. On the x-axis, I want you to put R. Now, what we're going to do is we're going to use red to symbolize the Fg, or the output of Fg. We're going to use blue to symbolize the output in terms of G. Now, in the previous lesson, lesson 17, we found as the radius is small, Fg is high. But as the radius increased, we saw that it exponentially decayed. The force of attraction exponentially decays. The same relationship exists when we talk about the radius and gravitational field strength. As an object moves away from the surface, there's going to be this exponential decay in gravitational field strength that follows this along. So realistically, these should overlap one another, but I'm hoping that that shows just the general trajectory of this, where if we talk about attractive force being proportional to this inverse square, then gravitational field strength is also proportional to the inverse square of the radius, and both of them follow that same principle. Now, with these ones, we do not want to assume moving forward that just G is always 9.81. That is not true. In kinematics, the reason we said that was because everything was close to the Earth's surface. Now that we're going to potentially move to other planets, or we're going to be shifting it throughout space and time, we don't want to have this just general 9.81. Gravitational field strength is now a dynamic value within dynamics. Lastly, I would just have you look at this here and just read over this before any sort of given assessment. And it's just a remember statement based on a summary of all the things we've talked about. So first and foremost, gravitational field strength is the same as acceleration. And so the way it's written in the notes, we could say that G is equal to AG, or acceleration due to gravity. Like either one of those is fine to write it as, but it's not the same as gravitational force. Really, really critical line here. Not the same as gravitational force or something measured in newtons. Now, for the definitions, just make sure you give a read over these at the end of the lesson here, just to make sure you're okay with these. But gravitational field strength, or GFS, versus gravitational force, one is a weight, one is how objects accelerate near that. Now, let's do some practice problems, or let's solve using some practice problems. So with these ones, off the hop, they say the gravitational field strength, I want to highlight that right away, on a surface of Neptune, what is the gravitational field strength on the surface of Neptune if the mass of Neptune is this and the radius of Neptune is 2.48 times 10 to the 7? Okay, right away, you want to make sure you write out Gn for Neptune is equal to capital G, which is the gravitational constant, times mass of Neptune divided by the radius of Neptune squared. Okay, let's plug in values here. Gravitational field strength of Neptune is equal to 6.67 gravitational constant times 10 to the negative 11 newtons times meters squared divided by kilograms squared multiplied by the mass, which is equal to 1.03 times 10 to the power of 26 kilograms divided by, all in the denominator, 2.48 times 10 to the power of 7 meters, and then squared. Remember, it's very, very important you're looking for this. That's squared, because you're going to forget it. I guarantee there's going to be one or two of you, just like I was saying in lesson 17, that you may forget this value. Now, the other thing you want to be looking for is, just like lesson 17, when we talk about the mathematics in this part, it's not that complicated. To be honest, it's very plug and chug. We take it, we plug it into the necessary formula that's provided on the formula sheet. We make sure we include our units. The difficulty is just make sure everything is in the standardized units. Kilograms, meters. If it's any different than that, please be looking for that. But this one, it's good and it's good, so we can progress. Now, our gravitational field strength of Neptune is the following. We plug this into our calculator. What you're going to notice is that you can actually figure this out by canceling the units first and foremost to show that you should get something. So kilogram squared over, or kilogram over kilogram squared, one of those kilograms cancels specifically in the numerator. Meters squared cancel for both of these. Therefore, I'm left with newtons per kilogram. I plug this all into my calculator to get a specific value, and I end up figuring out that the gravitational field strength is 11.2 newtons per kilogram, which is also equal to 11.2 meters per second squared. Now, again, on an assessment, either one of those would be fine. I would treat them both as equal. Just make sure you are showing your units all the way through. Very critical. All right, let's move into number 2. Number 2 says, what is the gravitational field strength at a distance of 1.91 times 10 to the 7 meters above the surface of Earth? Right away, I would draw a picture of this one, because when you're like, oh, it's above Earth now, rather than just being talking about the general planet, what do we get here? So what we want to do is, I'm just going to draw the planet of Earth like this. So I'm just going to draw a circle right here. And I'm just going to make sure it's drawn a little bit better or more circular, just to make sure. There we go. Perfect. Now, I'm going to just label this as Earth, just so we're all on the same page here. Now, I'm going to draw a center point. This center point is going to go right here. And what I'm going to do on this diagram is I'm going to draw a dotted line out and say that this is the radius of the Earth. So whenever we go to our table of values, or whenever we look on the back of the formula sheet for the Earth values, we're going to copy this down as this is the radius of Earth from the middle to the outside, or from the middle to the circumference. But in this problem, what they said is, what is the gravitational field strength at a distance of 1.91 times 10 to the 7 meters above the surface? So the object, or whatever we're considering, is up here. And so I'm going to put a dotted line using a red dotted line and say that this represents the radius above the surface of Earth to where it's located. Now, what this would mean is that if I was to do just like a general circumference at that point, or a general outside, it would look like this. This is kind of the area they're looking, or the GFS in which they want us to consider, is at this region above Earth, what would the gravitational field strength be, no matter what part of the planet I'm on. So necessarily I could be like down here, or somewhere over here, or somewhere over here, but as long as it's on that circumference, we're good. Okay, now we're going to plug in our values to the equation, but we have to be very particular about how we do this. So we're going to say that the gravitational field strength is equal to G m1, or in this case, the mass of Earth, as I'm going to call it, divided by, in the denominator, I'm going to call it RE plus R above, all squared. Because remember, if we want the radius, or if we're talking about the radius of this, it's from the center of the object out to where they've requested. And so for this one, what I'm going to do is even symbolically use this notation here and say that this is my radius total, or that's the radius I'm going to be using. Okay, now let's plug in some numbers here. So this is going to be G, or gravitational field strength, is equal to 6.67 times 10 to the negative 11. We want to make sure all units are here, newtons times meters over kilograms squared, multiplied by the mass of this, which we know the mass of the Earth is on the back of the formula sheet, 5.97 times 10 to the power of 24 kg. Close the bracket. Perfect. And then this is divided by, here's where we got to be careful, all in brackets, 6.37 times 10 to the power of 6 meters, which is the Earth's radius, plus the radius that is from the surface above. This is the 1.91 times 10 to the power of 7 meters. And then remember the squared. I'm telling you right now, and I keep saying it, I feel like a broken record, but that squared that's in the denominator on the outside here, just make sure you add both of those terms together, then square it here. All right, now according to this, if we're above by that distance, or we're above by 1.91 times 10 to the 7 meters above Earth's surface, the gravitational field strength, well, just by using prediction, the farther I am away from the Earth's center of mass, I'm going to realize that the gravitational field strength decreases as I go further out. And in fact, we're actually going a significant margin away from the Earth's surface, or from the middle of Earth, as I should say, or from the, I guess, no, we could say from the outside, because it is the radius, in fact. So because we're going such a significant margin above the Earth's surface and measuring gravitational field strength, as we know from previously in lesson 17 and lesson 18, when we broke apart this relationship of the inverse square law, it said that as the radius grows, the gravitational field strength exponentially decays. And so when I calculate this, I end up getting a value of 0.614. This is newtons divided by kilograms, which is then also equal to 0.614. meters per second squared. Now, if you compare that to Earth's gravitational field strength right on the surface, it's 9.81 meters per second. So as you can see, this is exponentially decayed to the point that it's very small in relation to if you were on the surface of Earth, meaning your acceleration towards the center of Earth is very low at this distance. All right, now part B continues this and says, what if we want to consider that a person weighs 400 newtons on the surface of Earth, meaning their FG is 400 on the surface? What would this person weigh at that distance above Earth, or in that section where they're above the surface of Earth by that distance? So how much would they weigh here, or what would their force of attraction be at that region? Now, to do this, first and foremost, when you're not given mass, we need to calculate that. So we're going to go Fg is equal to mass times gravity. And because this is on the surface of Earth, when we go mass is equal to Fg divided by g, the g is equal to the surface gravitational field strength. So mass is equal to 400 newtons, which is the person's weight, divided by 9.81. And rather than using meters per second squared, I'm going to use newtons over kilograms, which is the alternative approach, because it shows that the newtons cancel and I'm left with the mass. Now, mass is equal to 400 divided by 9.81, which is equal to 40.7747 kilograms. And I'm just holding on to as many decimals as I can, just because until we actually get our final solution, we should be holding on to as many as we can. Now, if this was, and I'm even going to put this in brackets here, if this is at the surface, so this is the surface of Earth, then when we go to above the surface, we're going to redo this calculation where we say Fg is equal to mass times the gravity. But instead of just this, I'm going to call it Fg2, or I'm going to erase this and just back it up a little bit here. I'm going to write this as Fg2, which is equal to mass, which mass does not change. No matter where you are in the given situation, or whether you're X number of kilometers above the surface of Earth, or you're on the surface, or you're on a different planet, mass never changes. What does change is your force of attraction and the gravitational field strength, depending on distance. Now, from here, I just want to get specific with this and say gravitational field strength number 2. And I'm going to call it 2 just because it's symbolic of the gravitational field strength from above, which was this 0.614. Now we plug the numbers in here. Mass is equal to 40.7747 kilograms multiplied by the gravitational field strength at that region, which is 0.614. And I'm going to, again, write it as newtons over kilograms. Reason being is because now I can show that my kilograms and kilograms disappear, leaving me with the newtons, or the force that is in this situation. So therefore, Fg2 is equal to, and if I get a specific value here, it's going to be 25.0 newtons. And we could say that this is for when you are above the surface. And so in the first part, if that was directly on the surface, now we have this new force of gravity, or this new attractive force, which is symbolic of 25 newtons. And so remember, in the grand scheme of things, when I zoom out here, if a person weighs 400 newtons on Earth, we should expect to see their newtons drop when they go above the surface, because the radius between the two objects is increasing. The body and the Earth were originally directly connected, and then now you're taking that person and bringing them away from Earth. The radius between those two objects increases, thus the force of attraction decreases, and more importantly, it exponentially decays. Okay, now in terms of this last problem, it's going to deal with proportionality, and we're going to solve it very similar to the lesson 17 example where we did this. The only difference is here is now, instead of gravitational force or force of attraction, we're going to deal with gravitational field strength. What I'm going to do is a very similar approach. First and foremost, we're going to say that we're going to write out our original equation, which says that GR, or on planet R, the gravitational field strength is 5.67. So I'm going to write out the equation, big G mr, which is the mass of planet R, divided by the radius of r squared. Okay, we know this is equal to 5.67 newtons over kilograms. And remember, that could also equal meters per second squared, but commonly they'll write it as either one. So newtons divided by kilograms. Excellent. What would be the gravitational field strength on planet Z if the mass of Z is triple that of R and the radius is half as much as r? Okay, so what we're going to do is do the following. Gz is proportional to, we're going to reflect the change in the variables here. And again, not equal to, but proportional. I always tend to forget to make that proportional, but we want to make sure it's proportional. G 3mr, because mz is 3 times the mass of mr, divided by, we're going to put in brackets, 1/2 times the radius of r squared, because they said that planet Z is 1/2 the radius of r. Okay, now we're going to write it as the following. Gz is proportional to, in the numerator, I'm just going to put the 3 out front and write this as gmr divided by, and then I should probably have the divided by on everything, so I'm just going to take that out and rewrite it. 1/2 raised to the power of 2 is equal to 1/4. So the 1/4 goes out front here. And then our radius of r, or radius of planet r squared, is just r squared. All right, now we want to highlight this front piece and then highlight the back piece, which is all the variables. Now the back piece here is actually just equal to that 5.67, or what we called our gravitational field strength of r. The front piece here, or this piece, is the reflection of the change. It's the proportional change that makes our gz. So gz is proportional to this change in gr. Now, to simplify that, what we're going to do is do the following. So just below, and just because I want to save space on the other side, gz is equal to, well, we know 3 divided by 1/4 is the same as 3 times 4, which means it's 12. And again, I don't want to put equals yet. It's proportional to 12 times gr. And then I'm going to arrow over here and say, now that we know the proportional change, gz is proportional to 12 times gr, we can now say gz is equal to 12 times the gravitational field strength of r, which is 5.67 newtons per kilogram. Okay, now what is this equal to? Well, as a value, when we simplify this, we should get, and I want to make sure I have the exact value, 68.0, and this is going to be newtons per kilogram. Again, you could make this meters per second, so just for the sake of the notes, I actually want to write it as 68.0 meters per second squared, because both of those answers are technically correct. I just want to make sure that first and foremost, we're doing newtons over kilograms, just because that's the way it was presented in the problem. Now again, to show this just like we did in lesson 17 in a slightly easier way, and a way that you could do on any sort of assessment and would be equally as marked, is this. Instead of saying gz is proportional to and including the variables, you can do the following. Gz is proportional to 3 times the original mass divided by 1/2 the original mass, all multiplied by this original gr. Because we're saying that gz is proportional to this change in gr. Now, if I do this, I'm going to get gz is proportional to 3 divided by 1/4, which is, again, 12 times gr. And then from here, you can just pass this answer and get the exact same thing. So 12 times, and you would just be repeating the same step here. So I'll even just draw little connecting arrows here and be like, then it would take you here, which would then get you to your final answer. So either way you want to do that. And again, this way of doing it is totally fine. If you would rather just reflect things in terms of a proportional change without all the variables going on so that it's a little more confusing, totally fine. I'm fine with you doing proportional changes in this manner, because it's also it's correct, and it's also a little more straightforward. For me, as like more of a mathematician mind, I like to show how it reflects in terms of what it does to the variables with the variables in the equation, and then pull it out as a common factor. But if this is way more simple, I would just be like, hey, gz is proportional to this magnitude of change to gr. All right, now you're going to want to get practice with these. So what they say first and foremost, and I need to point this out, use the data table from lesson 17. That data table was the one that had all the average radiuses, it had the periods, it had the masses. You're going to want to hold on to that table because it's really important for both these lessons in order to calculate things. So go back to that lesson 17 and just have it handy, even if it's on your phone or you're flipping backwards and forwards to that, that's perfectly fine. Now, again, as a big summary, just right before I end this, when we talk about gravitational field strength versus gravitational force, or lesson 17, was all about the attractive force, push or pull, between two objects with mass. Then, when we go on to lesson 18, it was the idea of, if I bring objects near each other, how does one of those objects accelerate towards the other? And how is that represented not only mathematically, but visually? All right, good luck with the practice. And then if you need help with these, always come see me right away.